Hi, my name is Adrian Fabris. I'm from the Geological Survey of South Australia. Now, I'd just like to start out by acknowledging that I'm presenting from the traditional lands of the Kaurna people. So in this presentation, I'll just give you a quick summary of some of the geochemical work we've been doing on IOCG deposits in South Australia. Okay, to provide some context, I'll be talking about the Olympic Copper Gold province that sits along the eastern margin of South Australia's Gawler Craton. It's most notable for hosting a number of hematite style deposits such as Prominent Hill and Carrapateena, and also of course the giant Olympic Dam deposit, which contains over 17 million tonnes of copper, and it's a very significant uranium deposit, a lot of gold and silver, and actually loads of other elements as well. But it's probably the primary example of the IOCG deposit. It's important to point out that the Olympic Copper Gold province hosts many additional occurrences. So there are in fact over 100 copper gold occurrences to varying significance, and over a range of styles. Geochronology that's been done at both hematite dominated IOCG occurrences and magnetite occurrences have shown that they form in a similar kind of time period associated with magmatism at around between 1600 and 1570. The basis behind this presentation really is a project by the Geological Survey looking at reassaying drill core held in government storage. So we reassayed select intervals from holes throughout this region, also collected spectral mineralogy using the Geological system and petrophysics. But it's the geochemistry that I'll focus on today, and really trying to answer a couple of just fundamental or basic questions of what are the minor and trace element characteristics of IOCG style mineralization in this region, and then also do deposits, the significant deposits, have distinct geochemical characteristics from those smaller occurrences. To define the geochemical characteristics of this style of deposit, we subset the samples into those either intersecting or within 10 kilometres of a known copper gold occurrence, and then subdivided that into those associated with hematite dominated occurrences versus magnetite dominated occurrences. And those and the samples and drill holes are shown on that map. I know you'll be hearing a lot about specific alteration facies in this webinar. So I'd just like to refer back to the Corriveau model and say that when I'm referring to hematite dominated systems, it's including a range of alteration facies that sit up around this part of the diagram of the evolution model. And really the magnetite dominated systems that I'm referring to encompass a number of different alteration facies in the earlier stages of the genesis of this style of deposit. In South Australia, most explorers are interested in the hematite style of deposit because they're far more copper endowed, and so the objective was really to try to see what are the characteristics that help you vector from magnetite style deposits towards hematite style deposits that explorers are in particular looking for. So before getting into the specific geochemical characteristics, I just wanted to point out that using regional geochemical data as we have in this study and insight from the alteration facies model, we can make some broad district scale observations. What I have done here is plot the ratio of potassic to sodic alteration in pie charts for each drill hole. So in pale yellow are samples with broadly similar K feldspar to albite ratio, which is typical of background rocks. Intervals which have either far more K feldspar than albite in orange and far more albite than K feldspar in brown. So if, for example, a hole was to have a narrow zone of albitic alteration, that will display as a small wedge of brown or sodic alteration in the pie chart. So while potassic alteration comes in at high temperature and is associated with magnetite-dominated deposits, what we tend to see is that drill holes in magnetite-dominated occurrences retain at least some sodic alteration phases, and so this type of plot effectively shows the distribution of where we get hematite-dominated styles, so in the central part of the Olympic copper-gold province, versus areas where we get magnetite dominated to those transitional styles, where we see at least some sodic alteration intervals in the drill holes. So where we have overprint of the two styles, I've tried to omit those drill holes. So that's just a footnote to the results coming up. Okay, just for reference, the results I'll be presenting are based on pretty extensive geochemical suite that utilise both 4-acid digests and fusion methods and a few other methods to achieve that 65 element suite. So we use spider plots to do the comparison and normalized values using the bulk continental crust defined by Rudnick and Gow, and did this because of the diverse lithologies in the data set. So considering 2 times crustal abundance is significant, and marked there with a red dashed line, magnetite dominated systems are characterized by enormously high values in the listed elements on the bottom right there, but in particular, in addition to copper gold, whole rock values around 10 times average values for selenium, tellurium, thallium and uranium. And also characteristic is a very clear, steep, light rare earth enrichment trend. Now with the hematite group overlaid, firstly the common elements to both hematite and magnetite group IOCGs are highlighted and listed here. What I've shown here are the mean values, but most convincingly when looking at means and median values are enrichments in the elements copper, gold, sulfur, selenium, tin, tellurium, thallium, uranium and light rare earths again. So given these data include a range of host rocks and minor prospects and deposits, we'd argue that these elements are characteristic of IOCG deposits more generally, or at least in the Olympic copper-gold province. In addition to these common group of elements, hematite systems have additional elements, enrichments, and I've highlighted those that are unique to hematite occurrences, as indicated by this study. So in particular, silver, bismuth, antimony and tungsten. While these elements could be viewed as the addition of external metal sources, we can do further analysis that suggests it doesn't have to be the case. So by categorizing the data by copper concentration, we can look at the behavior relative to increasing copper mineralization. So with the blue line here representing background and slightly anomalous with respect to copper, and increasing towards red, which is more than 3000 ppm, which is considered highly mineralized. So most elements become increasingly enriched with copper, as you would expect. It also highlights that these deposits can host a significant quantity of a range of metals. But And one of the interesting outcomes of this work, when we look at sample results from magnetite-dominated systems, the story is actually quite different. So while there are some significant enrichments, many elements actually get depleted with increasing copper values. So a number of the elements where the red represents the highly mineralized samples are actually below or depleted relative to background samples. But what is particularly interesting is that many of the elements getting depleted in magnetite-dominated systems are those that appear to be unique or highlighted as being unique to hematite systems. And these are now highlighted in red in the table. These involve a number of the chalcophile elements and a few minor elements. But what it indicates is that these elements are not precipitating with copper sulfides in magnetite-dominated systems, potentially related to the high temperature of the system at the time. But as the system cools and becomes more oxidized, they precipitate in ore zones. And an implication of this is that these elements can be used for mapping or vectoring towards lower temperature and more oxidized parts of the system. And this plays out when we plot the data spatially. So referring back to the figure I showed at the start on the right and comparing it to antimony values. So shown on the left is a perspective view of all the drill holes sampled in the project, with each downhole sample coloured by antimony. And it becomes clear that the same drill holes dominated by potassic rather than sodic alteration have high antimony values, and as alluded to earlier, represent the region dominated by hematite IOCG mineralization. So the other question that we asked ourselves from the outset was whether large deposits are geochemically distinct from the smaller sub-economic occurrences in this dataset, make up the bulk of the dataset. But in the dataset that we've analysed, we have some samples from Carrapateena deposit and Prominent Hill deposit, both hematite-dominated systems. So this analysis was for hematite-dominated systems. And we also incorporated extensive data, mono and trace element data from Olympic Dam based on published data from ERIC 2012. There's a lot of detail here, but basically we found a similar element association between the deposits and smaller hematite-dominated occurrences. And I suppose not surprisingly that the deposits contain significantly higher values for many of the associated minor and trace elements than their sub-economic counterparts. But particularly gold, molybdenum, rhenium, tellurium, uranium and light rare earths. But one of the key differences is that even in unmineralized samples, so those with less than 300 ppm copper, some elements, particularly light rare earth elements, are extremely enriched. So over 10 times bulk continental crustal values in light rare earths, lanthanum and cerium, even in weakly mineralized samples. So in comparison, for regional samples and in other prospects analysed, lanthanum and cerium values are typically less than 5 times crustal abundance in all but the most mineralized samples. So this was seen as a key difference, that common and extreme light rare earth enrichment. And so from an exploration point of view, it begs the question of where do we see values of 10 times continental crustal values for these elements. So using cerium for the comparison, as opposed to the antimony plot, using the threshold of 10 times crustal abundance, it really is only the deposits that are visible at this scale. But there are a number of interesting intervals identified in other holes in the region that warrant follow-up. So I'll just end with a couple of conclusions from this work. So at least in the dataset from the Olympic copper-gold province, Elements exclusively enriched in hematite-dominated occurrences can be used when exploring around magnetite-dominated occurrences to help find the more hematite-dominated parts of the system. Lastly, while economic deposits largely have the same element associations as sub-economic occurrences, the big deposits show significant enrichment in associated elements, even in samples that aren't copper mineralized. So in particular, light rare earth element values of more than 10 times crustal abundance appears to be a positive indicator that a significant system has developed. Okay, well, thank you for listening to my talk. And please contact me if you have any questions using the details on this slide. Cheers.